Okay, so do you see my screen, right?
Yes.
Okay. So today is going to be like the last lecture where I won't say anything really new, but it's still about classical theory of modular forms. But there's a few comments I want to make about things I forgot to mention yesterday. So first of all, I did define the discriminant function, so delta of tau. That was the definition. I didn't prove that it's modular. Well, it is modular, and in fact, it's equal to this thing in terms of, well, in terms of Eisenstein series of weight 4 and 6, which I also didn't prove they're modular, but I will prove that in a moment. Eisenstein series. So a comment that I wanted to make that I didn't make is that this thing has no zeros in the upper half plane. And so when I defined the modular J invariant, J of tau was a ratio of E4 cubed, well, by delta. So this thing is regular, well, holomorphic in the upper half plane. Because otherwise, if I divide it by delta, I might have gotten some poles. And that wasn't, I mean, I didn't look at meromorphic modular forms. Okay. And this is actually quite, well, so this non-vanishing is quite important. And it makes delta function very useful for changing weights in certain problems. So, because you can always multiply by delta or power of delta. So another nice thing is that you can take any rational power of delta. It's still a well-defined function on the upper half plane. So that will come into play maybe tomorrow more prominently. And another comment about delta. So I think I didn't make it, but it's worth saying. So the coefficients of delta are so the coefficients are usually denoted, and it's a terrible clash of notation, but you have to bear with it. So they're also denoted tau of n. So but tau has nothing to do with the variable. So this is called so-called Ramanujan's tau function. And Ramanujan, so he famously conjectured, although to him it was probably as good as a given fact, so he, I don't know how, at which point in his career he conjectured this, so did he care about proofs then or not? So two properties of this function, which are surprisingly deep. So first of all, it's so-called multiplicative function. So for any two integers which are co-prime, the value of it at the product is equal to the product of the values. And another thing is, well, so he looked at the values for prime numbers, and probably I think he also made a more general conjecture for arbitrary numbers. So, and he noticed, well, that curiously, they always seem to satisfy this inequality. Well, in fact, strict inequality for all p prime numbers. And I mean, these seem like innocent looking statements. So you can, I mean, basically you can write down the full statement of these two, well, two claims. So because you can just write down this power series here. And well, so both are amazingly deep things. So the first observation has led to what is called the Hecke theory, or theory of Hecke operators. Hecke operators, which is a fundamental theory of fundamental importance in modern number theory. And the second, well, the claim itself doesn't seem to suggest anything very deep, but it's, so the way that it was proven, so this was theorem of Deligne. In fact, two theorems of Deligne, which are completely different. And but it follows from Deligne's proof of Weil conjectures for arbitrary varieties, and plus another result of Deligne, which actually restates this problem in terms of algebraic geometry. So sometimes people call this result a theorem of Deligne and Deligne. Okay, but for me it will not. So these properties are far too deep, and yeah. So the most non-trivial property I will use about delta is that it doesn't vanish on the upper half plane. Okay, so now next I want to fill in the gap. So last time I defined Eisenstein series, and I said that they're modular, but I didn't explain why. And in fact, the definition I gave is not, well, in a sense, not the right definition. So I want to prove now that they're modular, and the right definition is the following. So I gave, yesterday I gave the definition by Fourier expansion. So I'll remind you, this is divisor sum of k minus first powers of divisors of n. And then these are Bernoulli numbers. Well, BKs are Bernoulli numbers. And so, but the right definition is the following. So there's a normalization constant, which you don't have to think about too hard right now about why it's chosen this way. But then it's a sum over a lattice. So you sum over all non-zero points in the lattice, and the thing that you're summing is this rational function. And so this is a definition. And now, and from this definition, it's actually much easier to see that it's modular. And then the actual work becomes in proving that these two things are identical. So the first definition I gave in the second. So I will just let me just verify that this is indeed modular. So I'll just ignore this constant. So this is something ck. So when you plug in this fractional linear transformation in the denominator, so now you can see that theta plus d to the k, you can kind of carry out of the summation. So it's some constant times theta plus d to the power k. So over, and now you just expand. So what you get is MA plus NC times tau plus MB plus ND and everything to the power k. And now what you do is you just, well, call this M prime and call this N prime. And you notice that since ABCD is a unimodular matrix, so it's a matrix of determinant 1, M prime and N prime again run over all integers. So this is the same constant times c tau plus d to the k times this thing, which is, I mean, it's exactly what we wanted to, well, what we wanted to prove, that it's a modular form. So it's c tau plus d to the k times g k of tau. And so now the modularity is kind of trivial. Then the question is, why does it have the Fourier expansion that I said it has? And this is an exercise in, well, so the difficult part of that computation is an exercise, well, in today's sheet. So, but let me just do this calculation. So, so what you use is so-called Lipschitz. Well, Lipschitz's identity. And you will now see where this funny constant comes from. So the identity is for k greater than or equal to 2, sum over all integers, 1 over tau plus n to the power k. So this is equal to minus 2 pi I to the power k divided by k minus 1 factorial. So it's almost the same, the inverse of the constant that we were using, times the sum from 1 to, well, the sum over L from 1 to infinity, L to the k minus 1 times q to the L. And q is, as before, it's the same. So it's e to the 2 pi I tau. So this is an exercise. And then using this, you can basically easily resum gk of tau is, so you split, so you have, in the definition, you have terms with m0 and m non-zero, and you basically sum them up separately. So the terms with m equals 0, so it's going to give you this thing. So this is m equals 0 terms. And then the rest, you just use this Lipschitz's identity, and you'll get a double sum of this form. And that's exactly, this is exactly, if you rearrange terms, I mean, if you resum this thing, you'll get divisor. Divisor sum function. And this thing is again, I mean, this is the identity due to Euler, but this is equal to minus bk over 2k. So the really, the right definition tells you immediately that this is a modular form, and then what you do is you compute what the Fourier expansion is. And then, I mean, this is much easier than starting with the Fourier expansion and trying to figure out why it's modular, although that you can also do. And here, so the other comment I want to make is, so this condition, well, I was a little bit fast here, but at some point I used the change of, so I had to rearrange some terms in the convergence series, and this is actually, well, important. So k is at least 4. Well, the important part is k should be strictly greater than 2, and for k equals 2, this doesn't work. So what this is, so what this means is G2, which if you think about the first definition, it's this expression, q to the n, but this is not modular. and it's not equal. I mean, it's not equal to the sum because the sum is not convergent, not absolutely convergent. So actually, when you define this sum, you can make it convergent, but then you have to be careful about the order of summation. And actually, when you look at the proof, at some point we change the order of summation, so that breaks modularity. So what you do is instead, so G2 is a very important object. It's not modular, but it's close to being modular. And what it satisfies, so G2, and I will use this group notation, so G2 minus G2 slash gamma. So if it were modular, this thing would be 0, but this thing is not 0, so it's some function of tau. And this function of tau is simple, so it's in fact a rational function. So it's 1 over, I mean, there's some factor involved, but the important part is this. So again, gamma is A, B, C, D. And so there are two ways of proving this. Both are somewhat unpleasant, but not very difficult. So first way of proving this is what is called Hege's trick. So you really want to start with a series, because that thing obviously has some modular properties, but it doesn't converge. So you fix it by making it converge. So you add this factor, which is absolute value to the power 2 epsilon. And and so you have some constant here times this. So you define G2 epsilon of tau as this expression, and it is modular in a more general sense than what we were discussing. So it's not holomorphic, but it is modular in the sense that if you apply fractional linear transformation with integer coefficients, you can work out what the transform series is. And then you work out exactly what the Fourier expansion of this thing is, and then what the functional equation is, and then you send epsilon to 0. And then you recover this thing.
Is the Lipschitz identity valid for non-integer k?
With some care it is, but here you actually have to use something more general because you have this absolute value. So actually this is a good place if you want to see this general identities of the Lipschitz type. So you can look in the Cohen and Stromberg book. They have a whole section about that. So, but I mean I don't really have much time to delve into details. And sorry, to dive into details, but there's another way of proving it, proving star, is, well, we know the generators of the modular group are S and T. So T, I mean for T, this identity we know because E2 is still periodic, or G2 is still periodic, so this is okay. And the real problem is how to prove it for S. And for S, well, you want to relate G2 of minus 1 over tau and G2 of tau. And there, so the trick is, you look instead of the Fourier series. So G2, if you ignore the constant term, it's a generating series for the divisor sum function. And so there is another generating series you can form for the divisor sum function, which is maybe more, well, easier to work with in some sense. So you can form a Dirichlet series. sigma and sum of sigma n divided by n to the s. And this Dirichlet series, you actually know, it's a product of zeta of s times zeta of s minus 1. And so what you can do is, you know that zeta satisfies a non-trivial functional equation, and this you can work out what this expression here satisfies. So functional equation relating s and 2 minus s. And then you can, well, you get the functional equation relating G2 of, sorry, my handwriting getting unreadable, G2 of IT and G2 of I divided by T for real values of R. And what you do is you do inverse Mellin transform. So, I mean, again, this is very sketchy, but this you can, if you have some experience working with Mellin transforms, it's not a very difficult exercise. So there's two ways of seeing how G2 transforms, and I mean, both are a little bit technical, but not too bad. Okay, so that's about what I wanted to say about Eisenstein series for now. So E2 will come back as a G2, or you can also have E2 with the same convention that you normalize the constant coefficient to be 1. Sigma n q to the n. So this will reappear later on, because this function appears quite a lot in the universal optimality proof and some other more general functions, like which are called quasi-modular forms. So, but that I will explain on Friday probably. And so what I want to say next is I will say more about theta series. And this would be probably, well, the first geometric applications of modular forms. And so, so let's recall, I already used it at some point. So let us recall the Poisson summation formula. So we have a lattice, well, contained in RD. And we don't, at this point, we don't assume any lattice. So any lattice doesn't have to be integral, doesn't have to have any nice properties. And so Poisson summation formula just tells you that, well, there's several formulas which people refer to as Poisson summation formulas, so they're all essentially equivalent, but they have different levels of generality. So this probably is the most commonly known one. So the summation of the function over the lattice, you can express as in terms of summation of the Fourier transform over the dual lattice. And then when you have shifts, you have to add a modulation on the right-hand side. And so this has a simple corollary, well, which people also call Poisson summation formula, which is if you set x to 0, then the sum of the values on the function side over the lattice is equal to the sum of the values of the Fourier transform over the dual lattice. And so what we want to do now is we want to pick some nice function f for which we know both f and Fourier transform and see what this tells us. And probably the nicest thing you can do is you take f to be a Gaussian. And the reason why this is so good is, so if you compute the Fourier transform, it's again a Gaussian with a different parameter. And you see that this, well, clearly it has something to do with modular forms because this transformation appears -1/tau. Well, the only problem, it gets multiplied by, well, again, this maybe is the reason why you would see this automorphy factor appearing. So this is, morally, this is the same as this c tau plus d to the power -d/2 for A, B, C, D DS matrix. So 0, -1, 1, 0. Except there's this power of I, which makes life more complicated. But as we will see, this actually plays an important role. And so what you can do is you can now restate, well, Poisson summation formula. So Poisson summation formula now implies the following identity. So I haven't defined the objects appearing in it, but I will define in a moment. So there's some function that one associates to any lattice, and this function called the theta function, it satisfies the transformation property of this type. And so what is the definition of theta lambda? Well, I kind of already implied what it is, and I mentioned it yesterday. So it's the sum over V in lambda of Q to the power V squared divided by 2. Well, I mean, you might not like it because if the lattice is arbitrary, these are in general real numbers. But then you can also write it this way, which maybe is a bit cleaner. Okay, and so what we get is, well, this is the Poisson summation formula. So now let's use it to prove something non-trivial. So using this fact that the theta series of a lattice has this kind of duality between the lattice and the dual lattice, so we can say something very strong about even unimodular lattices. So let's assume that lambda is now not an arbitrary lattice, but in fact a nice integral lattice, but even more. So let lambda be an even unimodular lattice. So I'll remind you, so unimodular just means it has covolume 1, and even means that the square of the norm of every vector in the lattice is an even number. Well, let's say in RD, then, well, first there are several statements, but one of them is kind of maybe a bit surprising. So the D has to be a multiple of 8. And the theta series is not only it has this duality, but it actually is a modular form. And it's a modular form of weight d/2. And so let me tell you how the proof goes. So we already kind of know a little bit. So we have this non-trivial transformation property here, which more or less tells you that if everything works well, so if t is divisible by 8, then it will be a modular form. But let me spell out the details. So first of all, lambda is even and unimodular. Well, this implies that covolume is 1, and the lattice is self-dual. So this means, so if you look at the at this non-trivial like transformation property here, we get minus d over 2. So there is no, so this covolume is 1, so we don't care. And then the lattice is equal to its dual, so it's again the same function.
Sorry, Danylo.
Yes?
Why is the lattice self-dual? Sorry if I'm being slow.
So this is a general fact about even integral unimodular lattices are self-dual, and even implies integral. And you just look at the definition of dual lattice. So if the lattice is integral, its dual lattice contains the original lattice. But also if you look at the covolumes, if the covolume is 1, then the dual lattice has covolume, the reciprocal of that. And then you kind of get you get a sandwich between the two. So if you look at double dual lattice, the dual lattice is sandwiched between the two, but the covolume kind of has to be, since we know it's 1, it's actually equal to the double.
So it's a fairly simple exercise.
Yeah, it's an exercise.
Thank you.
But even also implies integral, this is also a simple exercise. So if you only have norms that are even numbers, then all inner products are integer values. Okay, so this is what we get, and now so if d is so since lambda is even, this implies that v squared over 2 is an integer for every v in lambda, and this implies that the theta function is 1 periodic. And so what do we have? So if we knew already that d is divisible by 8, then this condition would exactly tell you that the function is is a weight d over 2 modular form for S transformation. This will tell you this invariance property for T transformation, so you would know that it's a modular form. And the reason is because like this I will disappear. So I to the d to the 2 is 1 if 8 divides d. But the fact that this nasty, like this multiplier comes in, actually forces d to be divisible by 8. And the reason is, so you can do a small calculation. So look at this expression here. So if you use periodicity, so this is equal to theta lambda of -1 over tau divided by 5 minus d over 2. And now if you use this property here, this is just theta lambda of tau again. So you look at this identity, and you see this transformation tau going to 1 minus 1 over tau is 3 periodic. I mean, it's is of period 3. In the sense that if you repeat it 3 times, you get again tau. So you can write this identity. So triple star. So write triple star for tau 1 minus 1 over tau. So you make the substitution in there and write it down. And 1 minus 1 over 1 minus 1 over tau, which is equal to 1 over 1 minus tau. So you write these 3 identities and you multiply them together. And so in the end, so because theta lambdas, so this is cyclic, so this transformation is cyclic for 3, and you'll get both like the arguments, these 3 arguments will appear for theta lambda on both sides, once for each of the transformation. And so actually theta lambda cancels out from the identity, and you get this identity. And here it's again a small calculational exercise. So to show that this identity for arbitrary tau in H implies that 8 divides D. So you can basically, you can compute it by sending, say, tau to infinity and then working out what the argument of each of these terms is. And so, well, here's one small comment, I guess, which I should have said. So this, when D is an odd integer, this, you have to be a bit careful about what you do here. So this is always, you take it to be the principal branch of the square root. So this is a number in the right half plane, and you take the principal branch. So, and here, whenever you have these quantities, they are principal branches. Okay. So, yeah, so we kind of proved it. And well, the claim that it's a modular form is implicit now. So it follows from these two properties, from periodicity and this thing, double star. Okay, so that's pretty much all I wanted to say. Well, almost all I wanted to say about lattices, but let me say a little bit more. So another application. So extremal lattices. So an observation which one of the exercises actually implies it. So there's a nice observation about spaces of modular forms is that they have an echelon basis. So what does it mean? So it means if the dimension of the space of modular forms for gamma 1 is D, then there is a basis which is nice for computing with Q extensions, but otherwise is completely, I mean, arbitrary. So there is a basis such that f the J's function in the basis it has only one non-zero coefficient between 0 and d minus 1, and the rest of the terms are at least q to the d and higher. So that's why I called it echelonized basis or echelon basis. And so what this means, so this actually doesn't follow from the fact that the space has dimension d, but it follows from the formula for the multiplicities of zeros. So this is, again, a small exercise, but I mean, I don't even give it. I mean, we won't discuss it tomorrow, probably. So it's very simple. And so what this tells you, well, in particular, for any A0, A1, A d minus 1, there exists a unique function in mk comma 1, which has the initial terms in the Fourier expansion, well, the ones given here. And so in particular, there is a unique function called theta ext or theta extremal of tau in mk comma 1 such that it has the first coefficients are all 0 except the constant term. And so let me write what, so there's, in particular, there's also the D's coefficient here. So this D, I mean, this AD doesn't depend, so it's a little bit maybe terrible notation because it depends on K. I mean, maybe let me write it AK. So D is the dimension of MK gamma 1. So, and this coefficient, so there is a theorem So you can compute it, well, explicitly in each case that you look at, but actually you can compute some asymptotic expansions for this coefficient as a function of k. And Siegel, I think he was the first one who observed it. So Siegel has proved that this coefficient is positive for all k. And so why does it, what is the relation with lattices? Why does it matter? Well, what this implies is if you combine the result, the previous result with this thing, so if lambda is an even unimodular lattice in RD, well, this D has nothing to do with that D, so let me write R2K. Then there exists a vector whose square norm, a non-zero vector, whose square norm is at most, is strictly less than 2 times the dimension of the space of modular forms. So this actually tells you quite something very strong. And sorry, less than or equal. And so why is that the case? Well, so if this weren't the case, then if you look at the theta function of this lattice, you would have, I mean, if it were not true, theta lambda of tau would have 1 plus big O of q to the d plus 1. And so that would mean that AK would have to be 0. And so you get something very strong, and in fact, so the lattices that we're interested in, E8 and lambda E8, they're kind of extremal with respect to this property. And in general, extremal means that so in this so minimal norm is exactly equal to this 2 times dimension of mk gamma 1. And and it might seem that these lattices are extremely good for sphere packing, and well, in fact, we know in the first few cases that they are. But in general, there's a problem with this property, is that there's a theorem by Nolos, Adliska, or Adlishka, I don't know exactly how to correctly pronounce his name, and so on. So there's only finitely many. There are only finitely many extremal lattices, and they give an efficient upper bound for what is the largest dimension, and it's quite large. And unfortunately, there's very little we know so about existence of extremal lattices. So and that's a big open problem. So how far you can go in classifying them. And the proof actually, so I won't say anything about the proof, but the proof basically, you look at this theta x of tau. So we know that it has so that any extremal lattice has the same theta series. That kind of follows from what I was talking about before. And so what they do is, to prove the theorem, is actually they compute. So Siegel computed AK in some asymptotic fashion, and they compute BK, and then they show us that at some point this thing is negative for large K. And then that means that it cannot be a theta series. But this is basically so Other than that, we don't know how to rule out existence of extremal lattices. So if this coefficient is positive, then we don't really know whether it exists or not. I mean, in small dimensions, there are some results. Other than that, no. And so maybe let me finish with something that will be useful in the universal optimality part of the course. So one thing that if you don't particularly understand why J function is interesting, so there's one way maybe which you will appreciate. So J tau gives an explicit conformal map. J of tau gives an explicit conformal map from the fundamental region that we were working with, from this region here. And so don't make this picture yet. So I will destroy it in a second. So there's I and rho. And so J maps this thing to a cut complex plane. So let me do a picture. So it actually maps this thing below. Let me use a different color. This thing it maps above. And since I have, I mean, I can also tell you what, so it sends I to 1728, and it sends this arc here to this segment here, and well, it also sends this arc here to the same segment, so it glues them together. And well, I don't know, maybe I can use another color. So, and it sends these bits to here. So, and then this punctured. So let me erase something. So so this is, I mean, it actually maps this thing homomorphically. So it's the only, the boundary components are sent to this cut from -infinity to 1728. And this actually, I mean, is useful. So when we discuss constructions of modular integrals, you can reinterpret many things in terms of very simple Riemann-Hilbert type problems. And then having this picture in mind helps quite a bit. So the J invariant just unfolds this fundamental domain onto C, and then it glues together everything. So yeah. And so to the last bit, so I'm running a little bit over time, but the last bit I want to discuss before tomorrow is modular forms for gamma 2. And so I'll just remind you, so these are matrices A, B, C, D congruent to the identity modulo 2. And so, so first of all, I mean, there's also a nice fundamental domain for this group. Looks as follows. So it's similar to what we had before. So it's a strip with some disks removed. And so this is a fundamental domain. Or well, maybe since I used, but this is like F2. So I'll just list a few facts. So some of them are given as exercises, but it will be useful to know them. So first of all, the dimension of the space of modular forms is now doesn't have this complicated behavior modulo 12, so it's just k over 2 plus 1. Next, so there is M. So if you look at the ring of all of these, So you again take a direct sum of all these spaces. And then this is polynomial ring in two, again, in two modular forms. And so I haven't quite defined them yet, but let me define them here. So there's three theta series that are, whenever you're working with modular forms for gamma 2, they're very useful to have. So they're defined as follows. So there's another nice property about this that is quite rare for modular forms. So the nice property that I'm talking about is that all these functions also don't vanish in the upper half plane. So, and the reason why it's kind of a little bit of a coincidence. So this is what the so-called Jacobi triple product theorem essentially tells you. But in here, you can also explicitly write them in terms of eta function. Well, this is not z, sorry, this is 2 tau, 8 of tau. This is also tau. And this is 8 of tau over 2 squared divided by 8 of tau. So I'm almost finished. So the claim is that theta 2 to the 4, theta 3 to the 4, and theta 4 to the 4 are modular forms of weight 2 for this group. And maybe just a small comment, so I forgot to mention. So if you have a function which is modular form for gamma 1, there's a cheap way of producing modular forms for gamma 2, which is you take, you rescale the variable. If you take tau over 2 or 2 tau, these are modular forms for gamma 2. And this is, again, a small exercise, but it's very easy to do. So these three functions are three modular forms are weight 2. And actually, any two of them generate the ring of modular forms as polynomial ring. So, but in particular, these two do. But they satisfy a non-trivial relation, which is so-called Jacobi's identity. So these are all in the exercise sheet for today. And finally, so the last thing I want to do is there's an analogous map, conformal map, also given by a modular function. So you take theta 2 divided by theta 3 to the 4th power. And this map, so this is so-called modular lambda invariant. So it has some applications in complex analysis, which maybe I'll mention later, maybe tomorrow. But what it does, it sends again this fundamental domain. So it sends it to plane with some cuts. And so this dotted line now goes to the interval between 0 and 1. And now let me again do this coloring. So now the right part of the domain is sent to the upper half plane. The left part is sent below. And so this bit here is sent to this ray, and the semicircles are mapped to the ray from 1 to infinity. And so, in particular, I mean, so this application I was talking about in complex analysis. So lambda gives a universal cover from the upper half plane to c minus 0 and 1. And then you can use this to prove, for example, Picard's little theorem that the entire function that emits two values is constant. But yeah, but this character will appear later. So it plays an important role in the constructions for the universal optimality. Okay, so now I'm 10 minutes late, but let me stop here.
Okay, thank you very much. Are there questions? Okay, so then I'm going to stop the recording.